In this video tutorial, we will be talking about constraints. But before starting that, let me tell you about those little three nifty icons here, the add-ons to the graphic interface of fullrmc. And those tell you about the version of fullrmc you're running and the computation package that are enabled in this license. This here is the single computation package, single frame, and this one will be given by default to all licenses. In addition to this, this license has the statistical computation and the mesoscopic computation. We will be running both of these in this tutorial to demonstrate constraints. So I am logged in and I am using here 10 license tokens, and I will be needing those. That's why I logged in using 10 license tokens. And I have no engine loaded and I have 0 engines in my account. So let me start by creating some engines. And I would like to start with this one, which is an engine that I will be loading from my local drive. And that's a nano, I'll give it the name, nano particle underscore silicon oxide. So let me create this and follow here along with the logs to see what's going to happen. And it's going to tell you how it's building that engine from the previously exported engine. So what I did is I created the engine in this interface and then I exported to my local drive, and now I'm emulating loading it back from my local drive to the cloud. I'm doing that on purpose just to show you that. So now this is done. I will go about creating 2 different engines because I will be using all of these. The first one here is the molecular underscore THF, which is tetrahydrofuran, and that's a molecular system. And give it a second, that's done. Let me now do the third one, which is the atomic nickel titanium. I bet you guessed it. Atomic underscore nickel titanium. All of these examples also are provided in the open sourced version of fullrmc that you will find on GitHub. So now I have 3 engines. Let me load this one here. And this is an engine of a nanoparticle, and it contains a multi-frame with 10 subframes into it. We will get into that. So let me also describe this engine for you because probably this is the first time that I'm using it. This engine has no boundary conditions. So this is about a nanoparticle that is isolated. And the way you have this in the experiment, you need to think about it like if you have a nanoparticle in solution that you're measuring, and the solution is very dilute. So one would measure the solution itself with the nanoparticles and will collect a diffraction pattern. And then you take the solution without the nanoparticle, so the solvent, and you would measure the solvent alone, and you subtract both to end up having the diffraction pattern of the nanoparticle alone, or the nanoparticle systems alone. This is the way that is actually done. And to simulate that, because the solution is very dilute, so the nanoparticles have no interactions between each other, that will show up in the diffraction pattern. So to simulate this in fullrmc, you would create a system that is not periodic. This is a system that we call here infinite boundary conditions. So there is no boundary conditions that are set, and the system is isolated in space. So you would imagine that the nanoparticle is alone in this universe, and you want to simulate that. So let me go here to constraints. The initial graphic interface here that you see gives you a little bit details about what you see in front of you and what you can do, how to create and add a constraint, how to update it, how to remove it, how to plot it. We are going to go about doing that step by step. So as usual, the right side section of this interface is the current state of the engine. And in this engine, in the frame size distribution /9, so the subframe 9 of the multi-frame size distribution has 3 constraints defined in that engine. A paired distribution constraint, an intermolecular distance constraint, and an atomic number constraint. So you can select any of these constraints and see the sum of the parameters and information about this constraint. So by scrolling up here to this one, for example, you see that this is a paired distribution constraint. It is used in the engine because you can set the constraint to be used in the engine to compute the standard error or not. The number of tried moves and accepted moves are 0 because I've never run that engine before. I just loaded in front of you, so there is no moves recorded here. And the standard error is none because it's not calculated yet. To choose and to add a constraint, you click on this drop-down menu and it shows you the list of constraints that are available in fullrmc. You have two types of constraints. You have the experimental constraints. So for example, here the paired distribution function, the paired correlation function or paired correlation constraint in that regard, structure factor and reduced structure factor. I will show you the difference between these in the documentation. And in addition to the experimental constraints, you have the physical or chemical constraints. For example, here the intermolecular distance constraint and the intramolecular distance constraint. This simulates the van der Waals forces, and it does it by setting a hard cutoff threshold distance between atoms, even intermolecular or intramolecular. You also have the atomic coordination number constraints that you can use to emulate an exact experiment, for example, where you have the number of neighboring atoms within certain distances. And also you have the molecular constraints that are bonds angle constraints, dihedral, and improper. We will go one by one about these. Let me start by the paired distribution constraint. So before doing that, allow me to show you what the paired distribution is. I'll go to constraints and I'll go to the paired distribution constraints. So let me show you a plot about it. This is how it would look like in general. And you need to make sure that the experimental data you are bringing in follows the formula that you see in here. Respect the formula that you see in here. You need to compare apples to apples. And other than paired distribution constraint, you have the pair correlation constraint that is little g of r. The distribution constraint is big G of r, and you have little g of r that is in here, and there is a relationship between big G of r and little g of r, and that's the relationship where the paired distribution constraint is equal to 4 pi rho 0 r paired distribution constraint minus 1. So they are similar to each other in some sense. They are related to each other pretty much. And you need to know that at low distances where the local density, atomic density is 0, the remaining quantity here is 4 pi r rho 0. And rho 0 here is nothing else but the average number density of the system. And this is a very important information that you can see in here. So 4 pi rho 0 r, this quantity here, is nothing else than this line here until you start having the first peak. And this tells you about the density of your system. The reason why I'm talking about that, because I always get that question when I answer some questions about the goodness of the fit and stuff like that. And the first thing I look at is the slope here, if it compares to the slope of the experimental data. And if it doesn't, it means that the density of your simulation, your simulated system does not really match the density in your experimental data. So you need to be careful about that. Now let me go back to constraint because I'm not coming back to this page again. You also have the structure factor constraint and you have the reduced structure factor constraint. Those are practically the same. There's no difference between the structure factor constraint and the reduced structure factor constraint except a factor of 1 or something like that. So there is a way to go from the structure factor to the paired distribution function, and this is via this formula here. So you need to make sure that your experiment respect that as well when you feed it a structure factor constraint. All right, so let me finish with that here and go back to the interface. And now we are ready to play with the pair distribution constraint and see how we can add it to the engine. So the first section here, I will highlight it. So this section end here is where you can load the experimental data file. And this has to be a 2 columns data file where the first column is about the distances. So the x-axis are distances. And the second column is the pair distribution function value. You can even load that by browsing a file or feeding it in here using a list of 2 lists. So that's an example here where the first list in here is the x-axis, so the distances, and the second list is the pair distribution function. Rebin is when you want to let fullrmc rebin your pair distribution function. So when your statistics are not good enough, you want to merge bins together. And a bin, just a reminder, is the width of an R. So if here the first number is 0.1, the second number is 0.2, the third one is 0.3, the bin here is equal to 0.1. What you can do is you can rebin these. In 2 cases, you need to do that. If the statistics are not good enough in your pair distribution function, or if the binning is not uniform. There are really rare cases where this is the case, and this comes from problems from the collected experimental data. But other than those 2 cases, you don't need to touch this. You keep it to none and you leave it. The third thing that you need to do, or the second in this regard, is setting the weighting. And you have a list of weightings that you can choose from. If you're doing X-rays experiment, it's X-rays. Neutrons experiment, it's neutrons. Atomic number is exactly the same as X-rays, but I put it here just for the fanatics about it. Neutron coherent B is the same as neutrons as well, so I leave it here for the same reason. And you have 4 other weightings here that I've personally never played with. So you set the element weighting that respects your experimental setup. So if you're doing X-rays, you choose X-rays. If you're doing neutrons in a nuclear reactor or an spallation source, you set neutrons. In addition to that, you can go about setting the elements weights manually. If you think, for example, you are doing, I don't know, if you're doing X-rays or neutrons for that regard, and in your simulation, in your simulated PDB file, you have hydrogens and you have deuteriums. Actually, you have only deuteriums, but you noted those all as hydrogens. And you know that the neutron coherent B for a deuterium is different than a hydrogen. So you want to change that and adjust for it. That's how you do it. You give the element name that matches the one in your PDB file, and you give it the weight. I think it's 4 point something if I'm not wrong. Maybe I'm off, I don't know. So here you can change the atom's weight 1 by 1 by the element type. Another thing you can do is to change the pairwise weights, and this is very important when you're doing differential diffraction. So imagine the case where you're doing a diffraction pattern and you are differentially removing carbon-carbon's signal. So you go about setting it like this, carbon-carbon, this is the element, and let me see, I forgot how to do it. Yeah, that's it. So you give it a dictionary or a hash map of carbon, and the value is the weight for that atomic pair, whatever you want to set it, 0, whatever. And you can go as far as you want to. You can go now, okay, I want my carbon and hydrogen to be at 2. I'm just giving stupid examples, so I'm sure you're following along. All right. This section here is about the data weights, and the data weights is the way fullrmc computes the standard error of your constraint. This section, this one here. So by default, every point in your experimental data has a weight of 1. If you want to put more emphasis towards a section of your experimental data or data points, give it more more weight into the total computation of the standard error, and you might have a reason to do that. It's because you want the fit to be better in certain locations. You need to specify it here. And to do that, you need to give a full list that has the same number of data points as in your experimental data, and you give the weight for every and each data point. So 1, 1, 1, 1, I don't know, and here you want it to be contributing twice to the standard error, 2, 2, 2, 2, 2.5, and so on and so forth until you finish with the length. If you don't give the same length, you would fail. Let me keep it like this. This here is where you set the scale factor between your experimental data and the model. So this will scale your model pair distribution constraints to your experimental pair distribution function. By default, it's 1, but you can set it to something else if you know that you need to scale up or scale down, or you can allow fullrmc to automatically set it for you by giving it a frequency of setting it. So this is a frequency in terms of accepted moves. By default, it's 0, so fullrmc would never touch it. Let's say I give it a frequency of 10, then every 10 accepted move, fullrmc would try to give you a better scale factor that goes between those boundaries, 0.8 and 1.2, and you can change those as well. I'll put that back here. Now here, the shape function parameter. This is a very important parameter, extremely important parameter actually, let me rephrase, that will take into account infinite boundary conditions. If you do not have the shape function set in place and your boundary conditions are infinite, you would see a drop in the intensity of your pair distribution function. The way that fullrmc does correct for that is by computing a shape function array that behaves like a background signal that will be subtracted from the constraint to bring it back to where it should be. In this case, we must set it because we are dealing with an infinite boundary condition system. So you remove the none, and those are the default values. You can set them manually, and if you don't know how to set them manually, you can set it as an empty curly brackets, and fullrmc will take care of populating this by the default values, which are these. And you can later on update the constraints and set it to whatever you want. So these values are rmin, rmax, dr, qmin, qmax, dq. You can read more about these in the documentation and how often you want this shape function to update in terms of accepted moves. So by default, it's every 1,000 accepted move, the shape function will update. Here you have the window function. This is a function that you would be using to convolute your simulated constraint with, and you can do this to mimic, for example, a resolution function that you have in your experimental setup. Here you have the limits. So let's say your experimental data goes between 0.2 angstroms up to 30 angstroms. If you leave the limits to none, fullrmc will try to reproduce all of that. But if your system is not that big, and if you have a pair distribution function that goes to 30 angstroms, your system must be at least 60 angstroms in length. At least, and this is exaggerating, you have to be 70 or 80. If you don't have that much, so you'd rather limit the maximum in here or the minimum as well. So you can say, okay, I know my PDF goes up to 30, but I want to simulate up to 20. Okay. And here, this is where you set if you want to use the constraint in the engine or not, or set it aside. And you might be asking yourself why you don't want to use the constraint. And this is very useful when you want to free up the engine to shake up your system a little bit and setting it back in the future runs. So you might want to say, okay, I want to shake my system up a little bit and let it run freely. So I'll set this as not used, and I'll update my constraint. And the next time I would run my engine, this constraint won't be accounted to in the standard error. And this constraint would not be constraining my atomic system. So I'm not going to set this constraint because I have it here. Let me show you how to do it, how to update it. So you have two buttons. The first one is to remove the constraint from the engine. So you click here, it tells you if you want to remove it. I'll say no. And the second button here is parameters. So you use that button to update your constraint. So you can update everything except all of these. You cannot update the experimental data. You cannot rebin anymore. You cannot reset the weighting scheme. You can definitely reset the atom's weight, the pair's weight for differential diffraction. You can update the data points weights. This is the shape function. You can update that. You can update this. You can update everything. And once you're set, you click update, and the new values will be updated to the constraint. So now let me select this and plot it. So what we have here in red is the experimental data. So you see it. In black is the total coming from the constraint. It's a very bad fit because I haven't run the engine yet. And the dotted line is the shape function. You see how I was talking here about the slope. You see it in here. That's the slope. And it is kind of representative of the actual slope in the experimental data. It's not very clear here, but we might see better after. And if it's not a good slope, if the slope is not okay, if the density is not matching well, I need to come here and change it in the number density in here, in the infinite boundary conditions. If I'm talking about periodic boundary conditions, I cannot touch this because this would be defined by the number of atoms and the size of the system. This is infinite boundary conditions. I can change it, but I'm not going to do that now. So remember, I have this. The pair distribution function goes along the way. It fluctuates around 0. Let me come here and remove the shape function. I want to show you how the density would drop. I'll update the constraint. Now I'll plot it and look. So I didn't remove the shape function contribution, which will account for the density drop. And you see how this is dropping down, and I would have absolutely no way to bring it back. You would never be able to fit your system that way. That would be completely off. So in an infinite boundary condition system, you must set the shape function. I don't know it by heart. I'll set it as open curly and close curly brackets. I'll set it, and fullrmc will populate it for me. I can update all of these. The only thing I usually play with is update frequency. I've never had to touch these, really. So anyway, so here you can also export your constraint. Let me export that. Let me open it here and allow me to bring it to your screen because it's too big. So this is the constraint for the frame size distribution 9. You have all the values in here. You can take that and plot it in your best visualization software that you have. So we plotted the constraint for size distribution 9. We can now plot it if we have the statistical package, which we do here. We can plot the statistical constraint, and this will plot the separate subframes all together in one plot. Let me show you that. So you see how that worked. And so it's not that good. That's normal because we haven't run the engine yet, but we will do that. And let me do that here real quick before coming back. So we can see what's happening at least. And let me come here, and I'll be in this section. Don't worry about this. I'll have a tutorial about that. Let me just run it. So I'm running here the statistical package. Let me come back, give it some time to run. Maybe you'll hear my computer now ramping up. Okay, and you can also plot the mesoscopic constraint, and you can plot the distribution. We will get to that. So mesoscopic is when you have a mesoscopic system, and this is enabled when you have the mesoscopic calculation package, which we have here, but we're not running any mesoscopic simulation now. So it brings all the subframes together into one mesoscopic system, and it computes everything for you. So you don't have it now because we haven't run the mesoscopic system yet. So when you choose anything between statistical or mesoscopic and you export the constraint now, what will happen is you will have the exported constraint for all the frames together. And this gives you all the information of the engine, the frames names, the number of atoms removed in each frame, the scale factor for every in each frame, the standard error for every in each frame, the weights. Here they are all equal to 1 because I haven't run the mesoscopic system yet. So they are all equal. And you will get the constraint value for all frames, all the partials, everything. That's a huge file. You can put it in your preferred software to plot all of these if these plots are not good enough for you. All right, enough with this. The other constraint I want to plot is the pair correlation constraint. Okay, so I cannot do that because the engine is running. It cannot. So what I want to do now is to stop that engine. Here you have it. I stopped that engine. And the pair correlation constraint is exactly the same as the pair distribution constraint, exactly the same input, but the function is kind of different. So I'm not going to go through explaining all of these again. The structure factor constraint is also, you set up exactly all the same thing. You don't have a shape function here because you don't need it. We are talking in the reciprocal space, not in the real space. So here you have it. And the reduced structure factor constraint, it's about also a reduced structure factor. You also set the same things. If you want to read more about these in the documentation, you can come here. You can come up here in the documentation section and read about it. One little thing I want to tell you about is that fullrmc computes the structure factor or the reduced structure factor starting from the real space. So you need to set the histogram parameters. If you leave everything to the default values, which is none, none, and none, fullrmc tries its best to set those for you. I think it goes from 0 here to the maximum divided by 2 and gives a reasonable value of dr depending on the maximum of size of dr would be, I think the maximum Q you can get in here, related to the maximum Q you can get in here. And that's it. If this does not give you a very good result, you probably need to change dr to a smaller value and you would play with it. And there are a lot of examples in the open source fullrmc to show you that. Now, let's talk about the inter and intramolecular distance. This is where you would constrain the atoms from getting too close to each other at an intermolecular distance level or at an intramolecular distance level. It's exactly the same input. I'm going to describe this here. So the default distance would be the one that you set, where no atoms should come closer to this distance. And the second thing is the type definition, is where you would set the atoms type you want to set your definition with. So you can go by element or by name. And this is the element type in your PDB file or the atom name in your PDB file. And then you come and set the distance constraints definition here. So here you see it in front of you. You give a list of tuples or list of lists where the first two elements here are the atoms types, whether it's names or elements, and then the distance that separates those. If you do not specify a couple of elements here, the default distance will be the one used. You can also check or uncheck the flexible flag, and this allows your atoms to kind of break the constraints definition under the only condition that this constraint's total standard error improves. And you can set the reject probability in here that gives you the probability of rejecting the move if the constraint is broken. Okay, so let's say the atoms get a little bit tiny closer than 1 angstrom here, and if reject probability is 1, then the move will be absolutely rejected. If the reject probability is different than 1, 0.9, then you have 90% chance that the move will be rejected. And this keeping in mind that the move enhances the total standard error of the engine. You also set it here to used or not used. So let me come here and select this. I can definitely do the same. I can update. You see, this is the type definition is 1 is element. This is the pair distance definition. Flexible is checked. I want it to be flexible. Reject probability to 1. Reject everything that gets closer to whatever I define. And it's used. I can even plot it. And this is what I have. The total standard error of this constraint is 0. Silicon, I have that many coupled atoms. I don't know how many it is, like 5 million interactions here between silicon and silicon. Oxygen and silicon, oxygen and oxygen. All right. Now let's move to the atomic coordination number constraint. This is a constraint where you set the atomic coordination number between atoms. You also have the reject probability and the used. And here we will talk about setting the coordination number. And to do that, you need to give also a list of lists or a list of tuples where each tuple has 1, 2, 3, 4, 5, 6, and 7 elements in it. The first two are the atom's elements or names. The second two are the shells, so the coordination shell. So for example here, titanium, between 2.5 and 3.5 angstroms. I would allow between 5 and 7.1. I'm not sure anymore what I'm doing in here. Let me see the coordination number. So coordination number constraint. Coordination constraint, that's the atomic coordination number constraint. Let me see what this is all about. All right. Yes. So as I said, this is the first element, the second element, the core and the shell element. You have the lower distance, the upper distance, 2.5 and 3.5. You have the minimum number of neighbors, the maximum number of neighbors, and you have the weight contribution to the standard error from this shell. Yes, this is what I was missing. This is the weight. By default, it's going to be 1, but you can set it to something else. So see, I wasn't sure. I went back to the documentation, and now I can explain it to you. So to define this, you can even set the element name right away, or you can give it, as usual in fullrmc, a string, like you can see here, name, colon, AU, so gold. I can give it a keyword and a value, and fullrmc would know how to parse this and to bring it back to something like this. So you can specify also by name or by element, or you can give also a list of atoms indexes as core atoms or shell atoms. All right, so let me come here, see the parameters. For this simulation, the only coordination number constraint I have is between silicon and silicon. I want the shell between 1.8 and 2.6 to have between 3 and 5 neighbors. And the weight here is not existing, so it's 1. By default is 1. Let me plot it. This is it. So this constraint is broken in my current engine, and the standard error is 0.063. So the engine will try to fix for that in the moves that will be happening. Let me now load another engine so I can explain these. So let me know the molecular THF. So this one has paired distribution function. It has bond and bonds angle and improper. Okay, so bonds. Also, you set reject probability and used, and you set the bonds definition. And this is even a list of lists or a list of items where you have the first atom index, the second atom index. So those atoms are bonded, and you give the bond minimum distance and maximum distance. Or you give it a definition. The molecule CCl4, this is the residue name, atom name C and atom name Cl1, the distance between these, or the bond lengths, should be between 1.55 and 1.95. That's how it is defined. Let me check here the parameters. And this is the definition for tetrahydrofuran. See this? Tetrahydrofuran molecule has all of these bonds definition. Atom name O and atom name C1, so oxygen and carbon 1, the bond should be between 1.27 and 1.7. Let me plot it. This is the bonds. I will run this engine to show you how this will change. So look at it now how it is. The same for bonds angles. So reject probability and used, and you set the definition. The same here. You have 3 bonded atoms in this manner. You don't have 2. You have 2 bonded. You have 2 bonds and 1 angle between those bonds. So you have the central atom, the left, the right atom, and the bond and the angle in degrees. Or you set it as a definition for the molecule residue CH4, carbon H1, H2. So CH1 is a bond, CH2 is another bond. So the angle between those 2 bonds would be between 100 and 120. So let me see the parameters here. And this is the bonds definitions for THF. So let me plot this. See how it is? Then when I would run the engine, you would see how that would populate. This is the rigid system that I'm starting with. And improper angle, let me see here. So let me talk about dihedral first. The same, reject probability, used. And you set the dihedral angle. So the dihedral angle is a little bit more complicated. You need to check it in the documentation, but you have 4 atoms that are in play. You can even set those by indexes or by atom names, and you will be setting angles here to define the dihedral properties. It is going to be a little bit difficult to explain it here, but you need to go to the documentation. Let me show you that. Constraint, dihedral, and it tells you atom 1, atom 2, 3, 4, and it explains to you what are the angles in here. It tells you exactly what all this is about. The same goes for improper. It tells you what atom X, Y, and O are and how you set the improper. So improper, this constraint forces a molecule to be in the plane, and this is going to be used in the THF. So I will show you this. So similarly, you choose the atoms here by index or by name, and you set the improper angle range. So let me show you the improper here, parameters. So for molecule THF, atoms C2, O, and C1 and C4 must be in the plane. So those 2 planes formed between C2, OC1, and OC1, C4 cannot have a separation angle different than minus 15 and 15. So it should be between minus 15 and 15. And the same for this. Let me plot this. All right. So this is what I'm happening. Now I can be sure that the ring of THF is in the plane. That's how I can make sure of it. Let me plot that for you, visualize it. Balls and sticks, element name, add. All right. You see this THF molecule, this one here. I'm trying to, it's difficult to point. Let me see if I can find a better one. Yeah, it's going to be difficult like this. Let me go to one on the edge. This guy here, for example. This one. I can make sure that all of these 5 atoms are in the plane by setting the improper constraint. And I'll do that for all the other molecules. All right. So now what I would do, I will want to come here and run this engine for some steps. So this engine is running. Notice the standard error, how big it is, but I don't care. Let me see here. So what I want to show you is how this is evolving. For example, for bonds, look, the more the engine runs, the angle starts to populate between the limits I am setting, and that's neat. And you see the same here for bond angle as well. So you remember how it was like little strikes here and there? And you will start seeing by moving those atoms how these histograms are populating. Let me come to the pair distribution function. So that's a pair distribution constraint. The same here. So I'm still far away from what it should be, but we start having a bell-shaped curve, and you will see at the end of that simulation, maybe I will demo it in another video, that here you will have two lobes here that are very beautiful, that shows you two bell curves for the bonds distributions. And thanks to fullrmc, you are able to do that because you can set the bonds as constraints, you can set the angles as constraints. Look how it is populating. So here you start having the shape of two lobes already. We started by one or two stripes. It is coming together, and you have the intermolecular distance. The standard error here is 0. So remember, we set flexible to true, but reject probability to 1. So that would never go other than 0. So this constraint will never have any standard error because we were not letting it. Everything here is set to, the reject probability is set to 1. That's for improper. It's not moving much. Bond angle. See how it's taking shape here? The more you let it run, the better it gets. So the goal is not about forming a shape. The goal is about fitting your pair distribution function. And this is where you know where to stop, but you need to give it the rules of how to do that. And the rules are defined by the constraints. So you see here, I start having two lobes here. And this is going beyond the constraint limits because it started before that. It started outside of the constraint limits. So when you want to read this plot, you see the limits here, 95 and 135. And this is in dark blue. So you have it in dark blue here, between 95 and 135, the limits. And we have some bonds here that go below 95, that go to 92.4. This is the minimum we see. So that's not perfect. We have a standard error that is not negligible. But all what the engine is trying to do is to bring everything together. Maybe at some point in your simulation, you want to stop the engine and come to the constraint and release some of these. If you think that you set the constraint too harshly, you want to release it, so you should be able to do that by stopping the engine, checking the parameters, and releasing this. So here I will stop this engine. Did I show the... And I will come back to load another engine, which is nanoparticle in here. And I will continue running the statistical system. And the statistical system here is using 10 license tokens. So I'm using 10 CPUs. All the 10 frames or subframes are running now. So trust me, my machine is running non-stop. So I can plot the constraint, and this is for subframe 0, or I can go to statistical and plot everything. And when I plot it in single, subframe 0 is the one that is plotted because it's the used frame. When I go to statistical, it shows me all the different frames running separately. All right. So you see some of them are doing better than others, but those nanoparticles are different. So different sizes. I want to come here now and stop this from running. I'm not going to explain any of that. I would run the mesoscopic now. So I am building a mesoscopic system out of those nine subframes of the multi-frame. And what that would give me is a distribution of weights. So here we started. So this is really not the way to do it actually, but we are starting to try to create a mesoscopic system out of those 9 subframes. So currently frame number 8 is at 98% of my total system, and here I have 0.0 or 2%. because I didn't give it enough time to relax before. And this would change. So the statistical is here, it's still the same. And the mesoscopic now is something else, is the mesoscopic system coming all together. So I'm not going to get into a lot of details here, but to show you that with different compute packages, you can do completely different stuff with the same engine configuration.